Hello, Calc 3 students, and welcome back. We are doing line integrals, and specifically I just boxed the definition of how to perform a line integral, and this is how you perform a line integral over a continuous region, okay, which is contained, or it contains a smooth curve. Of course, the smooth curve is this C here, okay. This is a smooth curve. What do we mean by smooth? Well, that means that it has like none of those like super jagged edges, and we can evaluate a derivative at any point on it. Okay, and here we've talked about the idea that ds is not fun to deal with, but if I can get like dt, I feel really confident, right? So although this might look more complicated out here on the right, this actually makes it much simpler because I only have one variable sitting in here, whereas I would have a bunch of different x, y's, and z's. Okay, and it's illustrated actually down here in my first example. So if you haven't had a chance, please do write down this example. And we're looking to calculate or evaluate the line integral, this thing here, where we have C is the line segment from the origin to a three-dimensional point 1, 2, 1. All right. It could be very helpful to attempt to draw such a thing. Again, I say attempt. I'm not the greatest artist, but I will do my absolute best here. I have my x, y, and z coordinate system here. And, well, how big do I have to go? Well, it's 0, 0, 0 to 1, 2, 1, so I think 1 up, right, in each direction, and I need 2 in the y. It's not too bad. Just the xy, it's 1, 2, so it's like this region here, right? That's the only xy part of the plane that I care about. And then z, I have to go up. Well, here, I'll try, again, I'm going to try my best to draw this. I have 0, 0, 0, this is this point right here, and I would be traveling to 1, 2, 1. Okay, 1, 2, 1 goes up. This is really tough for me to draw, but it goes up, right? And again, it just kind of depends on how you want to try to draw this, but it does go up. This thing is hovering. So if I'm thinking about it, this is hovering right above that point there. And I am drawing my line from here to there, right? That's my path. And again, this point, remember, is hovering. I've tried to draw the little dot in there. So hopefully you can kind of get a feel for it. And I have to do this because it's telling me the line segment, but I have to get r, right? I have to write r of t, where this is a vector with only t's in here, right? Specifically, I'd have 3 components. Well, here, you have to be clever. I do have some videos over how to parameterize a line. Please go check those ones out if you're struggling to parameterize a line. But this one here is not too terrible. If I let t equals 0 at the start, then I need to get the point 0, 0, 0, right? And if t equals 1, then I need my endpoint, which would be 1, 2, 1. Of course, that's arbitrary. You can pick whatever t value you want. You really can. It's just a way of scaling it. And what will be absorbed will be this, right? My velocity here, essentially. But we don't have to worry about it too much. I really like to do 0. I like to do the start. This is like quote-unquote the start. This is the end. And now I'm just thinking about, like, how could I write r so that I would get this thing with just t's, right? Well, if I want t to be 0 and I need 0, 0, 0, well, if I just had all these bt's, I would get that, right? But the issue comes up down here. If t equals 1, down here, if I have t equals 1, I'm going to end up getting 1, 1, 1. I don't want that. I want 1, 2, 1, right? Oh, okay, well, maybe I need just a 2 in here. And then I would have it. Okay, of course, this is 4. T is between, not 1. It starts at 0 and goes to a 1. Okay. And again, you could write this differently. You really could. You could write this differently and have different bounds of t, but this is by far the easiest way to represent r. And after I do that, now I could find r prime of t, which is just the individual gradients, right? This is just 1, 2, and 1. We're going to need that later, so I might as well get it now. Why do I need that later, you might ask? It's right here, okay? And I think I feel like I'm ready to plug in to my integral. Well, it's supposed to be from a to b. Well, a and b are my time constraints, so that's 0 to 1. That's not terrible. Then I go, and I plug in f. Well, f is this thing right now. So that is something squared minus something plus 3 times something. Okay, and then if I'm converting this, I have to have the square root, right? My x prime squared plus my y prime squared plus my z prime, oh, I don't need a z, whatever z prime is squared. And then this will be dt. And please don't be freaked out by all the blanks, right? I'm simply using this formula up here and just not filling in the stuff because I'm going to here in a second. I know that my x portion is just this t. Oh, so t would go in here. Then I know 2t is my y portion, and z is just this t. So I'm just plugging them in, right? That wasn't terrible. Next, though, I'm going after the primes. Oh, I already did r prime, right? That's this 1. Oh, 1's in here. Then I have 2. And then I have my 1 again. Okay. And hopefully that's not too bad for you to plug in there. And from here, now we just need to simplify this a little bit. This would be t squared minus 2t plus 3t times the square root of, well, that's 1 plus 4 plus 1. Oh, that's just 6 here, and that's dt. I feel decent there, right? I mean, I can simplify this maybe even a little bit more. I can take out the square root of 6 as it doesn't have any variables in it. T squared, negative 2t and 3t would make a positive t, then dt. And what's really slick about doing it this way, not only is there only one variable here, right, which makes the hand calculations very easy. Here we could use our calculator, right? And that'd make it easy because it's a finite integral. That'd make it super easy. Of course, we can do this by hand too. This is just 1/3 t cubed plus 1/2 t squared, evaluated from 0 to 1. Do not forget your square root of 6. Evaluate, okay, plug in the 1. I would have 1/3 plus 1/2 minus, 0 would just give me zeros for both of them. Well, that's 5/6, and I have to drop down my square root of 6, which means that this thing is 5 square root of 6 over 6. Okay. Now what's really crazy is this is the end answer, okay? But the crazy part is, if you would have chosen a different pathway, right, or a different parameterization here. So if I wouldn't have done it R like this, if I would have chosen, this is one option here, I'll write another one. R, I could have made be 1 plus 2t, and then 2 plus 4t, and 1 plus 2t. Like, I could have done that. I really could have. And if I would have done that, it would have been for my values of negative 1/2 to 0. Okay. And this will result in the exact same start and end positions, right? I have to start at 0, 0, 0. Here I'm going in, and then I go until that 1, 2, 1. and I would actually get the exact same 5 radical 6 over 6. Feel free to work that one out on your own and prove my point, but you can actually parameterize the line any way you want. It just make sure that you have the correct t values.